So, we were talking about the solution of the Schrodinger equation for certain simple potentials, and the last day most elaborately we have seen this case where bound states are formed and there is a the energy is negative, and as well the potential, there is a potential well, a finite potential well of certain height, and we have found out the energies corresponding to that. And these energies, as we have seen, these energy eigenvalues could only be solved using a graphical method, or it could also be a numerical method. And in that case, let me just plot a few solutions, or rather the wave functions for that problem. Okay. So, suppose this is the potential well, then this would be a even bound state, just one, and that will happen for for any depth, and then I am just showing 3 of them here. Maybe I will just make it a little bigger so that I can accommodate 3. So, this is your the lowest one, and then there will be another one which is like this. Okay. There is no overlap, it is just that you could space it farther apart. So, this one is one even bound state, this one is for the odd bound state as you see, and this one is again and this one is another even states. So, I mean in this, for this depth there are 2 even bound states and 1 odd bound state. Okay. And for a given problem I have solved these eigenvalue for this that kind of a problem, and have given you it in MEV for a physical case. Okay. Now, let me go over to another class of problems which is often very interesting in the context of quantum mechanics and also in classical mechanics. That is called as the harmonic oscillator, and because we are doing a quantum oscillator, so we will write a quantum harmonic oscillator. And what is meant by this is that there is a quantum particle which is executing simple harmonic motion, okay, and it is subjected to a Hooke's law kind of force, and then I mean there is a potential which is given by half kx square or half m omega square x square. Okay. So, it starts with the same formalism as classical mechanics. So, we have a f equal to minus kx that is acting on the particle. So, your m x double dot equal to minus kx. So, x double dot equal to minus omega square x, where omega equal to root over k by m. So, if you plot the function, the v as a function of x, it just looks like this, and as a function of x. So, there is a potential well that the particle is subjected to, and you are expected to solve the Schrodinger equation corresponding to this kind of a potential, which goes as so v of x is equal to half m omega square x square, where omega equal to root over k by m, and so on. And then we know that this has a minima at this point, and if you displace a particle, the particle will undergo a simple harmonic oscillation, and which you can very well understand by doing a Taylor expansion of v of x about this point. Let us call this as 0, x equal to 0, and you will see that if you ignore a constant term, then the the term which is linear in x vanishes because there is no external force that's acting on the particle, and the only term that survives is actually a half kx square, where k is given by the curvature of the potential, which is d2v dx square. Okay, and so we'll have to solve this problem, and that's what we mean by quantum harmonic oscillator, and we solve it just like all other cases. We'll solve it for one dimension, but I'll briefly introduce more than one dimension and explain that what is the um, implication of that. Okay, so this is the Schrodinger equation. This is the potential V psi, and that's equal to E psi. So E is the total energy of the problem, and we have to solve this. Okay, now this solution is not easy and cannot be done in a course which is at this level. So we'll skip the solution because the solution contains a large number of steps, and there are something like Weber's equation that you have to convert it to, and then you have to convert it to what are called as a Hermite's equation, and the solution will finally come out in the form of Hermite polynomial. These are special functions, and we don't need to know all of them in this course, but however it's important to know what the solutions are for both the wave function and the energy eigenvalues, and that will be all for you to know and remember, rather than the method that leads to that solution. As I said, that the solution is not too difficult, but however quite messy and requires you to know the tricks of, or rather the general methods of solution of second order differential equation, and the series solution in particular. Okay, so we will not solve this, but we'll show the energy eigenvalues which has a very simple form, which are called as n plus half h cross omega. Okay, so if you solve this problem, the E, which is let's then call it En, as n plus half h cross omega, where n is the quantum number. Okay, so n takes values. Now, quite interestingly, n takes values 0, 1, 2, 3 and so on, all integer values including 0. Remember, this is in contrast with the particle in a box which we have done, where n equal to 0 would have implied that the particle is not there at all, but here n equal to 0 is allowed, and that tells you that there is also a 0 point energy which is inherent to a system of oscillators and doesn't go away even for the lowest state that's possible, which is n equal to 0. Okay, so there is an energy that stays in the system which is called as a 0 point energy, and as you go higher up, that is as you increase n, you have energies that go to after half h cross omega is 3 half h cross omega, 5 half h cross omega, 7 half h cross omega, and so on and so forth. All right. The wave function looks a little complicated, but I'll try to at least make you. I'll write down initially all these factors, but these factors are not so important for us. And x, I hope you can see that. Okay, so the wave function has a slightly complicated form. I'll again write this here. Okay, in a slightly simpler form, we'll write it as some an, which is a normalization constant. We don't have to know that uh, in details, but that's a normalization. Then there is a term which is called as a Gaussian. Now the Gaussian is it's, you know, the Gaussian function is exponential minus alpha x square kind of term. So that's that exponential minus alpha x square kind of term. Then there is a let's call this as really as alpha, just to make things simpler. And okay, alpha x square by 2, that does not matter, that is fine. And this is exactly where alpha is equal to m omega by h cross, and so that is the form of the solution. You know that this is like a Gaussian is a function which is like this. Okay. Now, it is not only a Gaussian, it is Gaussian multiplied by a function, and the function is an algebraic function of x, where x is the position, which is half coming from that half m omega square x square, and the position variable basically. And and this particular function is called as the Hermite polynomials. It's just a name. You really do not have much to do with it, excepting that knowing that they are called as Hermite polynomials. But it has a nice property, and the property is that when n is even, it's an even function of x, and when n is odd, it's an odd function of x. Okay, which means that for n to be even, it contains terms which are like x to the power 0, x to the power 2, x to the power 4, and so on and so forth. And for n equal to odd, so this is n even, and for n odd, it's a term which has x, x cube, x5, and so on. Okay, so that tells you that indeed the eigenfunctions or eigensolutions of this problem clearly has a reflection symmetry, which is a property which you have told earlier is called as a parity. Okay, so the parity is the when x is changed to minus x, whether that function changes sign. If it does, we call it an odd parity state or an odd function, and if it doesn't, then we call it an even parity state or an even function, and that's what we have been talking about even in the bound state problem. Okay, so this gives you clearly two classes of solution, and these two classes of solutions are split into even and odd, and each even solution is orthogonal to the odd solution, and so on. So what I mean is that if I take a psi n and a psi m, this is going to be delta nm, which means they are going to vanish with each other, and that is because so this means that psi n star psi m dx is equal to 0 for n not equal to m, and this is equal to also 1 for n equal to m. And this involves a little complicated property of the Hermite polynomials, at least that normalization. We leave that at the moment. It's not important for you to know the mathematical details or these details of the Hermite polynomials for this given problem, but just to know that these have even functions of x and odd functions of x, and I'll write down a few of them at least. Like for example, h0 y, I'm calling that alpha x equal to y, some variable. Okay, it's equal to 1, h1 y equal to 2y, h2 y equal to minus 2 into 1 minus 2y square, h3y equal to minus 12 y minus 2/3 y cube, h4 y is equal to 12 into 1 minus 4y square plus 4/3 y to the power 4. I am doing it for completeness. You really won't need these polynomials for your calculation because we will not go details into that. But you see that this is an even function of y, which means y to the power 0, odd function of y, which is 2y, even function again, which contains y square and y to the power 0, which is just minus 2. H3 contains y and y cube. H4 contains y to the power 0, y square, y4 and so on. Okay. So, this is what it tells that that each one of the Hermite polynomials are also orthogonal to each other, which means that if you if you take the overlap of these functions and try to integrate them, so I am not going into the details, but there is you need to sort of look at those polynomials. They need an additional factor in order for them to be normalized. Not so important for us, but coming back to this here, where we have written down the energies and the wave functions, that part is the most important thing. Now you see the energies are, let me well, I would need the well probably. So I am writing down the energies, which is n plus half h cross omega, which means that the energies are like, so this is n equal to 0, n equal to 1, n equal to 2, n equal to 3 and so on. Okay. So they will simply keep going in unit of h cross omega, that is the between the successive levels, the gap is h cross omega, they are equally spaced, which is very unlike the problem that we have done for the case of particle in a box, where they are not equally spaced, rather between the two successive energy levels the distance, or rather the energy difference, goes as n square, which grows as n grows larger. Here doesn't matter what is larger values of n as well will give rise to the same energy value, and that's the difference between the two energy levels. Okay. So this one really looks like, so let me try to show you one some of this plots. So this is a Gaussian. Okay. It will penetrate outside the well just a little bit because they are Gaussian functions. They do not have nodes exactly at the boundary of the potential, but they eventually go to 0 at large distances. So this is the lowest wave function, because you see the h0 y is equal to 1. That's here, h0 y equal to 1, and which is what we have written earlier, and you multiply that by the Gaussian function, which is exponential, say minus y square, and then you get this. The second one is it's getting a little cramped, but doesn't matter. I mean, you can. So it is like okay. So this is n equal to 1 wave function. Okay, and you see what is the form of the wave function in the simplest form. If we forget about all of them, then it looks like x into exponential minus alpha x square by 2. That's this one, n equal to 1. Okay. How about this the second one? The second one is like this. Okay. So, this is n equal to 2, okay, and which has a form which is this Gaussian multiplied by some constant which is x equal to 0 and some function which is x square with some coefficients here. Okay. So, let us call those coefficients as a and b and so on, and of course, the normalization which I am not writing, I am writing down the bare function which will make you understand things better. Okay. So, this is n equal to 2 and n equal to 3 is again, it is going to be odd. So, that is like uh, and so this is again an odd function n equal to 3 and it has a form, if you like, it is like some a prime x plus some b prime x cube and then multiplied by the Gaussian. The Gaussian makes sure that outside the well the function goes to 0 and it is a product or which is called as a convolution of two functions. One is an algebraic function of x which has an even odd property and then it is multiplied by the this the Gaussian which is minus exponential minus alpha x square. Okay. If you take a mod square of this wave function, which means if you square it up, you will get the probabilities of how the particle is likely to be found in the potential well. If you plot the mod square of these, each one of those wave functions, they are anyway real. So, you can take the square of that and plot and you will get this I mean the probabilities of these corresponding to these states. Okay. Uh, there is a very nice which is often given an example for this to for one to calculate the 0 point energy, and it says I will state the question itself here. So, it says use uncertainty relation to find 0 point energy. And in this quantum harmonic oscillator. Okay. So, if you use the uncertainty relation and the question is that how can you find this? So, how do we find energy in any case? I mean energy after that will come to 0 point energy. So, that is the expectation value of H, this is what we have taught, and the expectation value of H means that we actually take the states, all these states that we have gotten, any state for that particular state it will give the energy, and this is equal to nothing but p square over 2m plus half, well I can take the 2m out, p square 1 by 2m and a half m omega square x square. That is the energy, and I can take this expectation within any state, that is n equal to 1, n equal to 0, n equal to 2, n equal to 4, 5, anything, and it will give the total energy of that state, which is the expectation value of this p square operator. P square is of course an operator, we have shown that earlier. So, p square equal to minus h cross square d square dx square, alright, and x square is actually the position operator. Okay. This a little tricky here. You see it is like this, that the classical mechanics puts x and t at the same footing. Okay, and here in quantum mechanics, there is no operator whose eigenvalues give time, but there is an operator whose eigenvalue gives space operator or space variables, which when acts on a state, it gives you the space variable. So clearly there is a little bit of ambiguousness in the way quantum mechanics and classical mechanics were developed, but then that's the question that we are going to address just a while, that even though we have been doing this x and t in a slightly different footing, but x is also a position variable. Okay, it's also an input, but it comes from an operator which is x operator, which is what we are taking an expectation value. So the expectation values are taken of operators. Okay, so how do we calculate p square? Because now we know that delta p square equal to p square average or expectation minus p average square, and similarly delta x square equal to x square minus x average square. Okay. Now, so this one is it is quite clear to see that for the harmonic oscillator, because it's symmetric about x equal to 0, the expectation value of x will be equal to 0, which is easy to understand, because the particle is likely to be either on the negative side of x or in the positive side, and p is also 0, expectation of p is also 0, because the particle can have velocities both equally likely to be in the left and in the right. So this is equal to 0, which means this is equal to 0 and this is equal to 0. So that leaves us to calculate p square and x square and so on. So if we try to calculate the h or the minimum value of h, then I will get this as which is E min, that is the 0 point energy, which is delta p square over 2m plus half m omega square delta x square, which is coming from this step where delta p square is same as p square average and delta x square is same as the x square average. I mean delta x square I mean x square average or expectation is same as delta x square. So the minimum would be coming from the uncertainties in momentum and in the position, and if you now use the delta p delta x is equal to h cross by 2, which is the uncertainty principle, and replace one of them, say we replace delta p, which is h cross by 2 delta x, and put it here in this equation. So your E min will become h cross square by 8 m delta x square plus half m omega square delta x square. And so this E min is a function of delta x, and if you take a delta E min delta x to be equal to 0, I mean delta of delta x to be equal to 0, and then you get delta x square is equal to h cross by 2 m omega, and if you put this value in this step, you get half h cross omega. Okay, so if you put it here, your E mean comes out to be half h cross omega. That's the minimum energy that we have said for n equal to 0. Okay, so it's quite interesting to get the minimum energy of the oscillator or the 0 point energy simply by using this this uncertainty relation. Okay, all right. So, let me come to something quite interesting anyway in quantum mechanics, that is called as degeneracy. Let me come to this part of the board. It is not specific to quantum harmonic oscillator, it can be for any problem there. And what it means is, let's understand what is meant by degeneracy. Okay. And by the way, degeneracy does not occur in one dimension. It's only a situation that occurs in more than one dimension, such as 2 dimension or 3 dimension and so on. So let us take a case which is particle in a box. We had drawn a box like this. We are still going to do that, but now we have a box which is like in a 3-dimensional box, which is just like you draw a box and so on. Okay, and this box is from say minus a to plus a in both x, y and z, or minus l to plus l, doesn't matter, or from 0 to l. So such that v is equal to 0 for 0 less than x less than l, and it's 0 less than y less than l, and also 0 less than z less than l. So it's v is equal to 0 for all these things. It's just extension of that particle in a box from 1 dimension to 3 dimension, because we are going to talk about a property called as degeneracy. And a priori, a degeneracy means that corresponding to the same eigenvalue, there are a number of eigenfunctions. So the different states or different wave functions have the same energy, but they are they are different. That is, the wave functions are different, and these wave functions are sometimes, I mean, most of these times these wave functions are orthogonal to each other. I have already solved this problem in 1 dimension, so there is nothing to solve this, but one has to understand that this psi is actually x, y, z. It just splits up into phi of x or phi 1 of x, phi 2 of y, and phi 3 of z. And they, each one of them, correspond to like a 1-dimensional wave equation or Schrodinger equation that we have written down, and the solution is simple. Now there are, corresponding to x, y, z, there are 3 quantum numbers which are called nx, ny and nz, and this is equal to nx square plus ny square plus nz square into pi square h cross square by 2 m l square. Okay, so as if the 1-dimensional problem is being triplicated in all the 3 directions. So this is what it is. Now you see that suppose your now the minimum value of nx, ny, nz is 1, 1, 1. Okay, it can't be anything other than that. Okay, they are nothing like 0. Now suppose you take n equal to total, say if this is equal to, so now you make one of them to be say 2. Okay, so then this nx square plus ny square plus nz square becomes 6, 4 plus 1 plus 1. Okay, but this 6 is not unique to nx being 2. It could be nx being 1 and ny being 2, or nx, ny both being 1 and nz being 2. But the wave functions are different. Why? Because the wave function is psi nx, ny, nz and is function of x, y, z. If you remember that we have its sine solutions, so it's a root over 2 by L, and now I cube it because there are 3 directions, and sine n pi x by L, sine n pi y by L, sine n pi z by L. Okay, so these are the things. So I'll put it as nx, ny and nz such that they are distinct. Now the wave function corresponding to nx equal to 2, ny equal to 1, nz equal to 1 will be sine 2 pi x by L, sine pi y by L, sine pi z by L. Okay, that's not same as 1 to 1, which will be sine pi x by L, sine 2 pi y by L, sine pi z by L. It is not again not same as 1 1 2, which is sine pi x by L, sine pi y by L, sine 2 pi z by L. Okay, but all of them correspond to an energy which is given by 6 pi square h cross square by 2 m L square. So it's said that all these 3 levels, that is corresponding to 2 1 1, 1 2 1 or 1 1 2, all these levels are degenerate. They have same energy but different wave functions. Okay, so that's that's what it means by degeneracy. And even in harmonic oscillator we can have such degeneracy. Let us see that. Again, we'll have to go beyond one dimension and start talking about 2 dimension or 3 dimensions. Let's just directly go to 3 dimension, and we'll then write the energy as which it would be nx, ny and nz, and which is like nx plus ny plus nz plus 3 half h cross omega. 3 half because 3 by 2 because a half coming with each one of the nx, ny and nz. And you can understand it well that it could be, the lowest values are 0 0 0, but if I take simply equal to one of them to be 1, the energy becomes 1 plus 3 half, which is 5 half h cross omega. But this can be done by taking this to be 0, this to be 1, this to be 0, or this to be 0, this to be 0 and this to be 1. And all of them will correspond to different wave functions, and these wave functions will have a exponential minus alpha x square by 2 plus a y square by 2 plus a z square by 2, and also hn alpha x, nx alpha x, hny alpha y and hnz alpha z. Okay, which says that the wave function corresponding to the upper choice, that is 1 0 0, is h1 here h1 alpha x, h0 alpha y and h0 alpha z, and the second would be the same energy, but the wave function will be h0 alpha x, h1 alpha y, h0 alpha z. And for the last one, again the same energy, it will be h0 alpha x, h0 alpha y and h1 alpha z. Okay, so this is the meaning of this the degeneracy, you can actually find out what is the degree of degeneracy, and you can let us see that how to find that, that what is for a given arbitrary n, how do we find the degeneracy. Let us do it for this problem. So this is equal to, so your nx plus ny plus nz is equal to n. Okay. So the degree of degeneracy will obey the relation, this relation, and if you choose nx first, so nx, if you choose, so nx equal to say 0, 1, 2, any of these things, then your ny plus nz, that's equal to n minus nx. Okay, because you have already chosen nx, which is some number, so your ny plus nz will be this. So there are n minus nx plus 1 possibilities for the pair ny nz. Okay, for that pair to be chosen. So why that is there? So let us see that if so this will be 0 n minus nx, which is the two possible values of ny and nz, or this will be 1 n minus nx minus 1. So that is ny equal to 1 and nz equal to n minus nx minus 1, such that nx plus ny plus nz is equal to n, and the second choice could, I mean the third one could be 2 n minus nx minus 2 and so on. Okay. So so the degeneracy now can be obtained as follows. So let's write the degeneracy to be Gn, and this is equal to nx from 0 to n for any value, and this is equal to n minus nx plus 1. This is what we have said, and this is I can just simply take this n plus 1 out, and I have to sum over 1 from nx equal to 0 to n. Okay, that's this term, this n plus 1 term, and then there is the nx, which has to be summed over from 0 to n nx. Okay, and this is simple. So this is equal to n plus 1, and nx from 0 to n would be n plus 1. Okay, because 0 is included. So this is n plus 1 whole square, and this one would be just that sum of n natural numbers. So it's n into n plus 1 by 2, and if you take a this thing, so n plus 1, if you take common, then it becomes equal to n plus 1 n plus 2 divided by 2. So if you want to know what is the degeneracy of n equal to 3, that's the third excited state. Third excited state will have a degeneracy which is 2 plus 1, that's 3, 3 into 4, that's 12 divided by 2, which is 6. Okay, so the total n being 2, which means that you can have it like this. Can we come here? So n equal to 2 will have a 6-fold degeneracy. That's what it says from the formula. Let's see whether that's correct. So you can have nx, ny and nz. It can be 1, 1, 0, or it can be 0, 1, 1. So all will give n equal to 2, or it could be 1, 0, 1, or it could be 2, 0, 0, or it could be 0, 2, 0, or it could be 0, 0, 2. These are the 6 energy levels, and each one of them will have a different eigenfunctions which are given by their Hermite polynomial. So, this will be Hermite polynomial H1 alpha x, H1 alpha y, H0 alpha z, and so on and so forth. Okay. So, this is meant by degeneracy. Okay. So, let me come to another quite important thing which is called as the time evolution of the wave function. Okay. Uh, of course, the way Schrodinger equation was written, we see that there is a possibility that we can evolve the wave function in time uh, and do it quite easily if h or the Hamiltonian is not an explicit function of time. Okay, it is only an implicit function of time, and we can take a, let me just wipe it out. So, time evolution of the wave function, or you can call it the wave packet, and so on. So, how do we do that? So, we can solve this equation which is d psi dt, which is now a function of, we'll write it as a function of x and t. I'm still continuing in one dimension, barring that we have talked about degeneracy in more than one dimension, and this is equal to h psi x of t, and this is the equation that you have to solve. We have earlier solved the time independent equation and did not want to find out what is the wave function at a later time. We have only found out or computed the wave function at time t equal to 0, and it can trivially be actually extended, but for that we have to understand how it can be extended to time that is not equal to 0, that is time greater than 0. Okay. Now, time and space are fairly decoupled other than relativity. Okay. And as I said over and over again, that we are doing non-relativistic quantum mechanics. So, there is no way that time and space would be related. So, we can write down this psi of xt as something that is function of only x. Let us call it a phi of x, and something that's a function of only t, let's call it a t of t. That would not be possible if you think of the relativistic mechanics, which it tries to intercouple or rather it couples the x and t degrees of freedom. Okay, so if I put it here, I get a nice equation which is 1 by I h cross divided 1 by t of t and del t of uh, t, because this ddt or del t, whatever I can write it. Once you know that there's a partial derivative, it's fine. So you can write it a ddt also. Okay, it's a partial derivative because you need to keep the x constant and differentiate t only. Okay, this would mean a full derivative. Okay, let's go back to the del. I think that's more correct in some sense. So it's 1 by t del t of t, because this doesn't, the t derivative doesn't touch the x, and we have h of which is a function of x. This is an assumption. H is not a function of t. If h is a function of t, then this method fails. Okay, and most of the time we see that h is only a time independent thing, which is p square by 2m plus v of x, and nowhere we have seen that v of x is a function of t, excepting for your those electromagnetic potentials you might have found the Lagrangian for electromagnetic fields, and in which case you have a velocity dependent potential, and velocity dependent potential is really something that's uh, it's not a conservative system, because velocity dependent potentials come in friction as well. Okay, so this is equal to phi of x divided by phi of x. Okay. Now you see that both these things are the left side is purely a function of t, the right hand side is purely a function of x. If they are equal, there is only one way that they can become equal, is both of them to be a constant e. I mean, I'm taking the constant to be E, and which is of course is the energy of the system, but this is the only way that it can happen, that one side is completely a function of t, the other side is completely a function of x, but they are equal. Okay, so if that happens, then from this I of course get the time independent Schrodinger equation, which is hx phi x equal to E phi x, which you've seen several times that we have solved, and which gives you a time independent Schrodinger equation. And then the other part, which is this one, is IH cross 1 by T of T uh, del T del T, this is equal to E. And I can rearrange this and write E as I mean this del del T as this is a del del T plus IE by H cross, and capital T of T is equal to 0, and the solution of this solution T of T is equal to exponential minus IET by H cross. Okay, so this is how you time evolve a system. That is, a system at time t equal to 0 would be evolved according to this. So if you take a wave function and multiply it by the by its by this quantity, and it is understood that this is in the sense that it is only evolving it with time, and the system has a well-defined energy which is given by E. Okay, and that E does not change with time. And you see that if I take a wave function, say, which is phi of x, and you multiply it by t of t, which is exponential minus IET by h cross, you only the probability is conserved, because for this wave function, if I calculate psi star psi, which is psi mod square, it will be phi x mod square, and that's it, because exponential minus IET h by h cross and exponential plus IET by h cross, they will cancel, and you will not get any you'll not get any factor coming out. So this is called as a stationary state, because the probability remains conserved at all times. Okay, so this is something that's this is how the time evolution. So if you are given a psi at t equal to 0, okay, if you need to know what is psi at t, okay, so you evolve the thing, you take this psi at 0, and it has a well-defined energy, and then t by h cross. Okay, so let me give you an example of this. Say for the harmonic oscillator problem, which is what we were doing. Let's come here. So for the harmonic oscillator problem, somebody has given you a state, say at x and t, which is equal to 1 by root 3 and psi 0 exponential minus I omega t by 2 and plus 2 by 3 square root psi 2x, this is a function of x, this is a function of x, and exponential minus 5I omega t, finding it difficult to write there. So let me just put it a line below. Okay, it's quite clear because we this is a superposition of state. So I've used a superposition that a quantum harmonic oscillator or a particle undergoing oscillation in a harmonic well or a quantum harmonic oscillation is found in this superposed state. This is a wave packet because I have superposed two of these states. This corresponds to n equal to 0, so it's a psi 0x, and that's why the energy is just simply half h cross omega. I have not written the h cross, but you can write it. I mean, there is also a h cross that cancels with this. Okay, so that's why it's written as h cross. I mean omega t by 2. So this has a energy which is half h cross omega. This has an energy which is 5 half h cross omega, and that corresponds to n equal to 2, because n equal to 2 will have 2 plus half h cross omega, which is 5 half h cross omega. Okay, so the question is that, so it is in a already a time evolved state, a superposition of state, and there could be many questions. So for example, one question is what is the parity of this state? Okay, so what I mean by parity is that, does it have a reflection symmetry, does it have a purely even parity or purely odd parity or a mixed parity? Here of course it has a purely even parity, because this is an even wave function, we know, because it only has a h0, the Hermite polynomial with an index 0, and this has h2, which both of them contain even powers of x, which means if you change x to minus x, nothing happens, which means that it retains the form. So it's an even parity state, and it will remain an even parity state for all times. Okay, we'll see such questions probably in the tutorial. Another very important question is that, what is the average energy? What is the average energy? And the average energy is given by psi h psi is equal to 1/3 E naught plus a 2/3 E2 and so on. And why it's 1/3? Because it's this coefficient square, mod square of this coefficient or square of this coefficient and the square of this coefficient, which this has an energy which is E0, which is half h cross omega. This has an energy which is 5 by 2 h cross omega. So this is E2, and which comes to the coefficient which is square of this. Okay, so it's an square En, that's the energy sum over n. That's the average energy, which let's call it as E. Okay, so this is that, and then you can just put it there. So it's 1/3 into half h cross omega plus 2/3 into 5 half h cross omega, and this is equal to nothing but 11 by 6 h cross omega at all values of t. So the time doesn't make a difference to the energy, and because it's a stationary state. Okay, so this it's a quick survey of a number of things that we have done, and let's stop here and carry on with some essential mathematical steps for the other class that we'll be having soon.